So now we are on to our last couple examples to go over regression, just to kind of get this whole process in your guys' heads. So if you could, dig out the regression analysis we did in our linear regression review in the first video, and we're going to be again looking at these anxiety scores compared to math test scores. So remember, we can always calculate a correlation and regression. What we want to know is if the correlation and regression model are statistically significant. And that's not just based off of, it's not just telling on our sample, but can we make a general description about our population? We also want to know what the model really tells us, and that's where we come back to our confidence intervals. So you have found the model, so we're not going to repeat that work here. If you need it, find the first video in this series, and what we found was our test score hat, or our predicted test scores, is equal to 91.65. That was our y-intercept, and minus 4.48 times our anxiety level. So that was our slope that we found. We wonder whether the weak relationship we see between anxiety level and math test score is evidence of an actual relationship. Or simply, is this just the appearance of a relationship that is due merely to sampling error? So how can we tell, is there something going on here, or is this just due to our specific sample? Maybe other samples get different results. So what we want to do is test the slope of the model. And anytime we're doing a test, we need to come up with a hypothesis. So we want to look at, here's our scatter plot. We have our correlation coefficient of negative 0.525. That tells you the strength. And we have our R squared, which is 0.275 or 27.56%. That tells you that the variability of our test scores is due to 27.5% of the time due to the anxiety level. So that's kind of a weak variability score. So does this hold up? And as you know, on our calculator, we pulled up both the scatter plot and our residual plot. So we need to now come up with a hypothesis test for this. So like always, if we're coming up with a hypothesis test with our slopes, we're going to say that beta sub 1, or the true population slope, is 0. There is no association between math test scores and anxiety, aka slope is 0. And our alternate hypothesis says there is a linear relationship between math test score and anxiety level. And the notation would be our beta sub 1 is not equal to 0, or our slope, there is some sort of slope here. So again, we go and check our conditions. So linearity, our scatter plot, as we look at our calculator, shows a definite linear relationship. Then we check our independence condition. So unless students are cheating, there's no reason to believe that test scores are not independent. So check and check. Then we need to pull up our residual plot, and the residual plot shows relatively consistent variation, although we do have that one outlier score. So we also, from our calculator, want to make a new document, and we want to make a histogram. So we're going to grab our residuals, and we're going to go to menu, plot type, and we're going to look at our histogram. Now, just as a refresher, we're going from almost negative 50 to positive 40. So we're going to say from our plot properties, histogram properties, and we're going to go to bin settings, and we want to equal bin width. We're just going to make that a little bigger, and our alignment is going to be, let's say, negative 50. And so you can see that we have a histogram of the residuals, shows sufficiently unimodal and symmetric distribution, although we do have that one little tail at the far end. So we should identify that there is a gap in the data. We should also, if you want, we'll do another statistical look, make a new document. We're going to make a data and statistics. We could do the exact same thing if you don't like a histogram, but we grab our stat resid and we could do a normal probability plot. So both of these give us a view of, is our residual data, again, this is the residuals, roughly symmetric and unimodal? Or does it fit our normal probability plot like a line? So this is good now. So we meet the conditions for a t-test with t sub n minus 2 degrees of freedom, or there is 24 different students in this, so 24 minus 2 is 22 degrees of freedom of the sampling distribution for the slope of the regression model. So we could go to the trouble of calculating everything by hand, but that would take a lot of time, so let's just go to our calculator. So again, we get control doc, and we're going to add a calculator here. And now, since we're doing a test, we go menu, 6, and then 7 for stats tests. And now we're going into this linear regression t-test. Our anxiety level is our explanatory or x variable, and our math test scores are our output or our response variable. It does save our regression equation into F2. We don't have any frequencies. And then our alternate hypothesis are both beta and this other Greek letter means rho, which is the correlation coefficient, are not 0. So if I hit OK, I get a bunch of values. So let's look at this. It says what our regression equation is. So we have a plus bx, where a is the y-intercept and b is our slope. And then we have what was our hypothesis test that we ran. So it gives us our alternate hypothesis saying that they are not equal. So both our population slope and our correlation coefficient. This is beta, again, B for beta. And this P little symbol is ROH, rho, for correlation coefficient for our population. Now we get our t statistic, which is negative 2.89. We get our p-value for our slope to be 0.008435. We get our degrees of freedom, which is good. And then we get what we found before with our regression model. We have our A, we have our B, we have our S sub E, or what the calculator will say is S. This is the sample estimate of standard deviations of errors. So S sub E, again, this comes up into quite a bit of formulas. It also gives us our standard error for our slope, which is useful. We give our r squared and we get our r value. And because our slope is negative, r is negative. And if you guys forgot, you can always take the square root of r squared, and then you just have to remember what the sign is. So let's put this together and say, well, just to confirm what we did, what I should see, if you were calculating this by hand, we would take our slope, negative 4.486, minus our hypothesized slope. So this is our null beta sub 1. And then a couple other things that we have below here. We have our standard error, or S, so this is our 18.6931, divided by, we have our standard deviation of our x variables. Now that's not given in any of our calculations so far. So how do we get that? If you go back to your calculator and we hit menu, we're going to do statistics, we're going to do stat calculations, and we just want one variable statistics. And so we're going to select the number of lists, we just want one. And what is our x value in this case is the anxiety level. That's all we need to say. And we get, if I scroll up just a little bit, S sub x, or the standard deviation for our x value, to be 2.51373. So I just put that value in, divided by the square root of n minus 1, which again, n was 24. It's really helpful to keep these values organized, and so you can find and plug them in. If you plug all of those into your calculator and you had to do this by hand, remember we're finding our t value for n minus 2, and we get negative 2.8932. So that's our t statistic. How do we go from our t statistic to our probability? Well, again, if you recall that we're doing a two-tailed test. So if we did our cumulative density function, so menu, 6 on the calculator, and then this would be our distributions. We want a TCDF. Our lower bound is negative whatever. And then our upper bound would be our t-score. So negative 2.8392. Our degrees of freedom for this is 22, or n minus 2. And we hit OK. And then we take that p-value and we multiply it by 2 because it is a two-tailed test. And again, that is exactly matching what our calculator has told us. So now we have to look at our t statistic and our probability, or our p-value that we got. So based off of our t-statistic of negative 2.8932 and our p-value of 0.0084, if we are looking at an alpha level again of 0.05, we reject the null hypothesis. And every time we reject the null, we then say there is sufficient evidence to believe there is a relationship between anxiety level and test scores, at least for this specific test. So then the question goes, well, if we reject the null, like we always do, can we build a confidence interval that describes what the actual or true slope is? So the question goes, so what is our true slope in this case? So again, if there is a relationship between anxiety and test scores, then the slope, our hypothesized slope, is not equal to 0. So what does it equal? We're going to use a confidence interval on our calculator. So now we go to menu, 6 for statistics, and now we go to 6 for confidence intervals, and we're going to do a linear regression t interval. We're going to do slope in our case, with our x list being anxiety and our y list being math test scores. We have a 0.95 confidence level. We hit OK, and we get our equation, a plus bx. We get our lower bound and our upper bound. We get our degrees of freedom. We get our S sub e, or standard error for our residuals. Standard deviation for our residuals. And then we also get r and r squared. And on our TI Inspire, we see that we get S sub e of slope. So that is S standard error for our slope. And we also get our margin of error. So if we are given the lower and upper bound, we are 95% confident the reduction in mean test scores at all values is between negative 7.7 points and negative 1.3 points for each unit increase in anxiety. So we're describing our slope as anxiety increases, the scores decrease our 95% confidence interval from these two values. Again, if we were to calculate this by hand, and I would like to see, at the very least, you write out this formula. And again, this is our critical value for n minus 2. We have, from our t-test, we have this as s. We found what this was, s sub x, from our previous values. And we know n minus 1, where n is 24 in this case. So our regression model slope said negative 4.4862. How do you calculate a critical value? Well, if you need a refresher, again, on our calculator, we hit menu, we hit 6 for statistics, and then we are looking at a distribution, and we're going to do inverse t, 95% confidence interval, so that'd be 0.975. Our degrees of freedom here is n minus 2, so it's 22. We hit OK, and we get 2.707387. And that's where we get this value right here. This again is s, this is s sub x, and this is n minus 1. And if you plug those into the calculator, we get the same values. So please give me the setup, at the very least, for our confidence interval, and then you can utilize what the calculator tells you. Again, the AP test loves seeing that you know what you're doing and not just regurgitating what the calculator says. More often of times, they're going to give you the work already displayed. And it's essential that you're able to read what the computer output says. So let's just go through one of these. And the last time we might have seen this was chapter 9 or chapter 10. And we were like, well, we don't need to look at a lot of this. So at the very top, it will always tell you what your response variable is. So if you remember back, we were looking at one of our examples this year. We talked about blood alcohol levels. It tells you what the dependent variable is, or the response variable. It will also give you your r squared value. Just ignore the r squared adjusted. Don't need it, don't care about it for our purposes. Now we have S sub e, or our standard error for our residuals. The calculator, or the computer, both, will tell you S instead of S sub e, so you should know that. We'll have 16 minus 2, so here is your n, and your degrees of freedom is 14. You might also see the letter nu instead of degrees of freedom, or df. Now, what else do they give you? Well, we have constant. This would be our y-intercept, and we have this as our predictor variable, or x, or explanatory variable. And then we have our coefficients. So we have our y-intercept. I'll just write these in. And then we have our slope. They give you those, and then right next to them is our standard error of our slope and our standard error of our, SE of B0 and SE of B1. And next to those are the t values, or the t ratios, for each of those. So if you're wondering how those are calculated, we take the y-intercept divided by the standard error, gives you the t ratio for the y-intercept. To find the t ratio for our slope, we take our slope divided by the standard error of our slope. And then the last bits are what's the p-values for each of those scores. Oftentimes we're looking at our probability for our slope, but it's good to look at what's the chance that both of these happen. So save this slide if you need an explanation, because the last problem that we're going to do just relies on giving you the computer outputs. So, last example for the school year. A least square regression analysis for seat location and achievement for 30 students gave the following results. So we have 30 students, so our n is 30. Now, we have our scatter plot, which shows a somewhat weak relationship. We look at our residuals, and we get score equals 85.7 minus 1.12 times rho. Now, this is our linear regression model, a plus bx. And we have our r-squared value of 0.04, or 4.7% of the variability in score is due to the rho variable. We also have our residual plot, where we see that it slightly tails to begin, but then it's mostly linear. So we might want to worry about those two scores on the side. And then we have our histogram, which is roughly unimodal and symmetric. So let's run through our conditions. So is our scatter plot, our first thing, linear? Yep, so the scatter plot shows a weak negative linear relationship. Remember, this is our SODS statement if we wanted to write it. The residual plot shows no pattern, which is good. Independent, so students were presumably randomly assigned to seats, and of course, we're not cheating. If they are, then we can't assume independence. Next, we look at our residual plots to check for normality. So the histogram of the residuals is sufficiently unimodal and symmetric. The normal probability plot is mostly linear, with those two values at the beginning, or in the -20 to -10 range. A little worrisome. Equal variance. The variation in the scores from each row varies, but the variance is sufficiently consistent, so there's no pattern. So you can see like dot, 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 dot in the residual plot. It's fairly spread out, so our equal variance condition is met. Now we have met the conditions, so we continue to the inference, which means our hypothesis testing. So our null and our alternative hypothesis. So now we're given our scatter plot and our computer output. So here is the output from the computer of our 30 students. We want to identify the standard error of the slope from the computer output and then interpret that value. It's not just writing down the number, but what does this value mean? And then we're going to calculate a 95% confidence interval and interpret that, and then see if this is convincing evidence that seat location affects scores. First thing, from our data, if we want to figure out our standard error of our slope, we look at our explanatory, or x row, and then we go to standard error. So this gives us our slope, and this gives us SE of B1. So we don't have to calculate that at all. So the standard error for our slope is 0.9472. Tells us right in the output. This means if we repeated the random assignment many times, the slope of the estimated regression line would typically vary by about 0.9472 from the slope of the true regression. And that's just how we interpret standard error. Next, we want to look at our 95% confidence interval. We can't use our calculator here in terms of doing it for us because we don't have the lists. So this is where you need to know what you're doing. So to calculate, remember, we do B1 plus or minus our critical value of n minus 2 times our standard error of our slope. That's the formula that we use. So our sample size was 30 students. So our degrees of freedom here is 28. Going to our calculator. In this case, I'll just make a new calculator so it's easier to see. So we will do menu, 6 for statistics. We want to look at our distribution and at inverse t. We're assuming a 95% confidence interval, so 0.975. And our degrees of freedom was n minus 2, or 28. So we hit OK, and we get 2.0484. So now we just have to fill in the values. Our slope from our chart, plus or minus our critical value of n minus 2, or 28 in this case, times our standard error of b sub 1. If we multiply those two, we get negative 1.171 plus or minus 1.94, which gives us a 95% confidence interval of scores compared to row selection from negative 3.057 or up to 0.8231. So there's our 95% confidence interval. So we should be able to interpret that. So we are 95% confident the true slope of the model falls between negative 3.05 and 0.8231. Now, knowing what we've known before from confidence intervals, is there convincing evidence that seat selection affects scores? And because the interval captures 0, or 0 is in our interval, we do not have convincing evidence that there is an association between test scores and row number. So that finishes up our inferences on regressions. I hope to see you in the office hours, and then we have one last assessment, and then we're going to prep for the AP test. Thank you for all you guys do, and I'll see you in our office hours. Peace.